Hello, good morning, gentlemen. Are you there? Can you hear me?
Yes, sir. Loud and clear, sir.
Good. If you can hear me, we can start. Okay. So we were talking about length and angle, and we last time studied the dot product, length, the Cauchy-Schwarz inequality, the triangle inequality, and I think, and also distance, and we stopped at orthogonal vectors and projections. So we will continue from there today, and let's see how much we can go. Okay, we stop here. Angles. So for non-zero vectors u and v in Rm, cosine of theta equals this, u dot v over norm of u times norm of v. As you see here, if you notice, it is n here, right? You're talking about vectors in n-dimensional space. And we are giving this as definition, not theorem. And this is actually inspired by this in two-dimensional space. Let's say we are given two vectors, u and v, in two-dimensional space, right? And let's say this one is vector u, and this one is, let's say, vector v. Vector u and vector v. So let's say the angle between these two vectors, because they form some vector, right? Angle, let's say it is theta. So how do we determine this angle, right? Actually, this theta, and to determine this angle, we need to, okay, dot B, all right. Okay. This is theta, and we need to all right. So we'll just use simple trigonometry here. Let's just join this vector. All right. From here, what do we see here? Let's see here vector v plus vector this. Let's say this one is vector x, right? So vector v plus vector x is equal to vector u. So from here we can identify, right? X equals u minus v. So this x equals this, right? And I'll just use the cosine theorem. If you remember from maybe high school or pre-calculus, if you're given a triangle, right? And this cosine theorem states that cosine of theta, actually this, let me just draw any triangle here. Let's say this one is C, this one is A, this one is B, this one is, this angle is alpha, right? Cosine theorem states that C squared is equal to A squared plus B squared minus 2 times AB cosine of theta. I'm just going to use this formula for this. So from here, C, it is our vector x here. A, it is the length of vector v. B, the length of u, theta, theta, right? At the time, we will have this equation. And what is x? X is u minus v. It's a vector. We need to take the length. So that is u minus v squared. On the right-hand side, a squared plus b squared. That is u squared plus v squared minus 2 times u times v times cosine of theta. Okay, unfortunately, I need to write this. Okay, here we have cosine of theta. Okay. So now I just simplifying this, we will get the thing. Okay, so from here, as you remember, what does it mean, this u minus v squared? As you remember, actually, we know that this u norm squared is the same as u dot u, because we know that the norm of u is defined as, what is it? Square root of u dot u, right? And using this definition here, we have u minus v dot u minus v, right? And if you remember, how did I expand this? You remember it's just equal to, here we have and u, right? Here we have norm u squared because of this minus 2 times u dot v plus norm v squared. And on the right hand side, we have this thing, right? So I see here u squared, they cancel each other, and v squared, they cancel each other. What we have here? On the left hand side, we have negative 2 times. Here we have negative 2 times u dot v equals on the right hand side, we have negative 2 times norm of u times norm of v times cosine of theta. Right? And if you just divide both sides by negative 2, they cancel each other. And here we have cosine of theta is equal to u dot v over norm of u times norm of v. That is the proof of this cosine of theta, the angle between these two vectors in two-dimensional space. Now for n, we have just generalized as a definition, because now how do you prove that? For example, for four-dimensional space and for five-dimensional space. So we're just giving this as a definition. For two-dimensional space, we can give as a theorem. So that is a proof. For three-dimensional space, when you just do this, we will get the same thing. Now we just generalize this to n-dimensional space. That is how we find the angle between two vectors. Actually, here it's not the angle, that is cosine of the angle. Now from here, we can find the angle, right? What is theta? Theta is cosine inverse of u dot v over norm of u times norm of v. Okay. Compute the angle between the vectors. Okay, we are talking about two vectors. Let's say this one is u. Let's say this one is v. And this angle, let's say it is alpha or theta. Because let's just find this in radian. Then usually we use theta for radian. Okay, to do this one first, we need to calculate two things, right? Number one is, first we need to know u dot v, which is -1, 2, 3 dot, here we have 3, 1, 7. And -1 times 3, -3, plus 2 times 1, it is 2, plus 3 times 7, 21, which is equal to -1 plus 21, that's equal to 20, right? And next thing is, we need to find the norm of u, which is equal to square root of 1 plus 4 plus 9, because -1 squared is 1, 2 squared is 4, 3 squared is 9. So that is equal to 1 plus 4, 5 plus 9, it is 14. And how about the norm of v? Norm of v is equal to 3 squared is 9 plus 1 plus 49, right? Which is equal to 1 plus 49, 50 plus 9, that is 59. Then cosine of alpha will be, if we have u dot v, that's equal to 20 over norm of u, that is square root of 14, times, and here we have square root of 59. And it says that find the angle, compute the angle, right? So to compute the angle, that alpha will be equal to, actually not alpha, I need to write theta here. Okay, will be cosine inverse, right? It is 20 over square root of 14 times square root of 59. And this thing, just using our calculator, we can evaluate this. So here we have shift, cosine, and fraction. Numerator is 20 over square root of 14 times square root of 59. Square root of 59. That's equal to shift cosine fraction 20 over square root of 14 times square root of 59. Or you close the bracket equals is about 0.8. But actually we need to change this into radian. So 0.801. Okay, 0.801 radian. But actually, you better write this in degrees, right? Actually, just change this to degrees, 3. So we will have 45.9. So it is about 46 degrees. Okay, that is how we find the angle between two vectors. How about in three-dimensional space? Compute the angle between the diagonals on two adjacent faces of a cube. Maybe for visualizing this thing, it may be a little bit hard because just drawing a cube and after that visualizing this thing. But if you just use coordinates, actual things get much, much easier. Okay. So it says that compute the angle between the diagonals on two adjacent faces of a cube. So if you just draw a cube here, here is our cube, and this face, they're adjacent to each other, or this face and this face adjacent to each other, or this face and this face adjacent to each other. It says the angle between the diagonals on two adjacent. Actually, if you just take these two faces or these two faces, actually all are the same thing because we know that it's just a cube. So let's just say it is just standing on the table. And if you introduce this coordinate axis, that is our x-axis, right? That is actually collinear with one edge of the cube. That is, let's say, y-axis. Let's say here, this one is positive direction of x-axis. This one is positive direction of y-axis, and that is positive direction of z-axis, right? And these are two adjacent faces. This face and this face. Adjacent means they have a common edge. This is a common edge to these faces, right? And how about the diagonal? We know the diagonal is a line segment that joins two non-adjacent vertices of a polygon, or here it is, what is it? Cube. So these two sides are adjacent, right? But these two vertices are non-adjacent. So that's why we call this diagonal. Anyway, so let's say that is the first diagonal of one face. That is another diagonal, right, of this face. And then the question is, what is the angle between these two diagonals, right? The diagonals of adjacent faces. Now, if we just introduce, actually, what is it? Coordinates, since it's a cube, right? Let's say this one is a unit cube. All sides are 1. At the time, the coordinates of, actually, if we just put this edge on the origin, right? And this one is, what is it? 1, 0, 0, right? And how about this point? It is 0, 1, 0. And how about this point, for example? It is 0, 0, 1. Why? Because x value is 0, y value is 0. Just I need to move up. And how about this thing? To reach this point, right, I need to walk along the x-axis. That's why x coordinate is 0. And y, we are not moving in the y direction and just moving up. And that's why y coordinate is 0 and z coordinate is 1. And how about this thing? That is, along the x-axis, we are not moving. That's 0. And now I need to move along the y-axis 1 unit. That's why y coordinate is 1. And along the z, right, that's why is equal to 1, right? So let me just write here, this vector, let's say it is vector u. And this vector, that's vector v. And then what are the components of vector u? this will be, that is OA, let's say, that will be 1, 0, 1. And how about the components of vector V, that is 0, 1, and 1, right? That's it. As see here, really, when we actually introduce coordinates, a lot of calculations get very, very easy. So from here, what is U dot V? That's equal to 1 times 0, that is 0. 0 times 1, that is 0. 1 times 1, it is 1, that's equal to 1. And how about the norm of vector U, that is square root of 1 plus 0 plus 1. 1 squared is 1, 0 squared, 1 squared, that's equal to square root of 2. And how about the norm of V? That's equal to 0 squared equals 0, 1 squared is 1, 1 squared is 1, so that's equal to square root of 2, right? Then what is the cosine of, let's say this theta here, that angle, that is U dot V, that's equal to 1 over norm of U, that is square root of 2, and norm of V, that is square root of 2, which is equal to 1 over 2. And we know that if cosine of theta is equal to 1 over 2, it's just a special angle, right? It's 1 over 2. That means that what is theta? Theta is 60 degrees. Then the angle between the diagonals of two adjacent faces of a cube is 60 degrees. Okay. Now, after considering these two examples, now let's talk about one important concept. As you remember, we are going to see this concept a lot. Orthogonal vectors. That is the special one, because if we talk about the angle between two vectors, they may form infinitely many different vectors, angles, right? The angle between two vectors, it may be any number between 0 and, what is it, 360 or 180. Okay, so among this, when it is 90, it plays a special role in linear algebra, and that's why actually it deserves to have a special name, that is orthogonal vectors. So two vectors U and V in Rn are orthogonal to each other if their dot product is equal to 0. That is, we are giving this as a definition. Okay, and also in two-dimensional space or three-dimensional space, we can prove this, right? Why? Because if you're given two vectors in two-dimensional space, right? And if two vectors are orthogonal, what does it mean? Orthogonal means if U is orthogonal to V, that means that the angle, right? The angle between these two vectors, let's say that is theta, that theta must be equal to 90 degrees. It means this. So using the definition, if you just write here cosine of 90, if these two vectors are orthogonal to each other or perpendicular to each other, that is equal to, what is it, U dot V over length of U times length of V. And what is the value of cosine of 90? We know that that's equal to 0, right? And these two vectors are non-zero. So from here, this implies that then U dot V must be equal to 0. Actually, here we have two-way implication, not only this, two-way. That means that if the angle between two vectors is 90, then the dot product must be equal to 0. Or if the dot product of two vectors is equal to 0, then the angle between these two vectors must be 90 degrees. Okay? Good. Show that the vectors U, 1, 1, negative 2, and V, 3, 1, 2 are orthogonal vectors. And how do you show that? To show this one, we need to show that their dot product is equal to 0, right? So we have to show that this dot product of these two vectors is equal to 0. What is UV? It is 1, 1, negative 2 times, we have 3, 1, 2, which is equal to 1 times 3. It is 3 plus 1 times 1. It's 1. Negative 2 times 2, it is negative 4, which is equal to 0. Since the dot product is equal to 0, that means that these vectors are orthogonal by the definition. Okay, very simple example here. Pythagoras theorem. Okay, why is this Pythagoras theorem? Because it looks like Pythagorean theorem in trigonometry or geometry. For all vectors u and v in Rm, all vectors, it says that, what is it? The square of the norm of the sum of two vectors is equal to the sum of the squares of the norms of those vectors. It means this. If and only if, that is important in math, is if and only if, we mean this. The symbolic representation is this. Okay, in short form of if and only if, that is IFF. That is written, pronounced as if and only if. U and V are orthogonal. Okay, what does it mean? That means that this thing is true if U and V are orthogonal. And U and V are orthogonal, then this equation must be true. That's why here we have two-way implication. Okay, this is a theorem. Theorems require proof, otherwise it cannot be used as a fact. So let's just prove first this way, okay, this direction. So that means that we assume that this is true, okay? And from here, we should show that this U and V are orthogonal. All right. So how do you prove that? Actually, we have already done a few times about this thing. We know how to expand this. We know that this norm of U plus V squared is equal to U plus V dot U plus V. And if you expand this, we know that here we get norm of U squared plus 2 times U dot V plus norm of V squared, right? And when actually this is equal to norm of U squared plus norm of V squared. When? When actually these two things cancel each other, if and only if this thing, right, is equal to 0. That means that this U dot V must be equal to 0, because these two things are exactly the same. When actually this thing is equal to 0, then these two expressions will be equal to each other. Otherwise, they will never be equal to each other. Okay? And so also in this way, we can prove this, the converse. We assume that U and V are orthogonal, right? That means that we assume that U dot V is equal to 0. Then from here, if you expand this, we will get this expression. Since U dot V is equal to 0, then this thing will be equal to 0. And what's left here? Only this thing is left. So that means that that's true. Okay, that's why it is called, what is it? Orthogonal, the Pythagorean theorem. Okay, projection, definition. Now we will talk about very important concepts. Before I continue here, okay. Before I continue here, let's talk about this. What is it? The importance of anyway. These projections we'll talk a lot, guys, and you need to at least study this well, if possible, after this lecture. Okay, this class, you need to have a look at your book and close it and try to get this formula yourself and try to understand what we mean, actually what we mean by projection of V onto U and how we obtain this formula and how is it used. Because frequently we are going to use this thing in the future. Anyway, that is really, really important concept, especially to find the closest vector or the shortest distance from one vector to another vector. So projection, it says that if U and V are vectors in Rm and the measure space, and the U is not equal to 0, then the projection of V onto U is the vector is some kind of vector, and we are just denoting this by this. We can just denote it as kind of vector P, defined by this. Projection of V onto U equals U dot V over U dot U times U. And these are all vectors. Okay. So that means that here we are given a kind of vector. Let's say that is vector U. And here we have vector V in n-dimensional space, right? and the projection of V onto U. What is it? If you just drop from the head of this vector to this vector, we get something here, right? It's placed here. So we are talking about this vector. And let's say this vector is vector P. So the vector P, actually, we are just defining this as the projection of V onto U. Okay? So we are talking about this vector. And that here is saying that that's equal to this thing. Why is it so? Y actually is equal to U dot V over U dot U times U. Okay. And to actually get this formula, first thing, I'm going to use this idea. Assume that's the angle between vector V and vector U. Let's say it is theta, right? And since it's a projection, we're just dropping a point from this to this, right? That means that this angle is 90 degrees. So as see here, we have a right angle triangle here. And using the definition of cosine here, what is cosine of theta? And we know that in a right angle triangle, cosine of theta is defined as the adjacent side, right, by hypotenuse. So here, don't confuse the vector. So when we say actually take the ratio, we need to take the length. So here we will have the norm of P over the norm of V, right? Now from here, if you just multiply both sides by the norm of V, we will get here the norm of P is equal to norm of V times cosine of, what is it, theta, right? Okay, that is how we get this. Now, another thing is, okay, I have V here. How about this cosine of theta? Let me just continue here. Equals, let me just write here, equals, okay, let me rewrite. Right. Then, if we just take this one, P, that P, right? What is P vector? Actually, we define this thing as P, right? This thing as P. I'm trying to get this everything in terms of V. What is P here? P is, here we have V, right? Here we have V. Okay. Here we have V times. Actually, what is P here? Here, this P. P is, I can just write here, this vector P, right, is equal to the length of vector P, that is the length of vector P. If I just multiply this by the length of vector P and the unit vector in this direction, it gives us the vector P. So that gives us the magnitude of P. And what is the unit vector in the direction of U? That is just equal to U over norm of U. Actually, it is norm of U. And we have already studied this, right? How to normalize a vector. What is this thing? It is a unit vector in the direction of U. So unit vector, if you just multiply this by the length of P, it gives us vector P, right? So at that time, this vector P, let me just write first, vector P is equal to, it is magnitude, right? Times, and here we have vector U over magnitude of U. Now, instead of this vector P, I can substitute this, right? I can substitute this. So I will have here, let me just write vector V, I mean the magnitude of V, and the cosine of theta, right? And here we have this thing, that is U over magnitude of U. And now, let me just express everything in terms of U and V. Here we have V, it is just a number. Let me just write it here, my norm of U, because this U is a vector. What is cosine of theta? Cosine of theta is, we have just evaluated there, right? Cosine of theta, it is the angle between these two vectors, V and U. That is U dot V over magnitude of U times magnitude of V. And what is up here? Here we have vector u. So here we have vector u. Actually, if you notice here, this is a scalar. This is a scalar. U dot v is a scalar. This is a scalar. I can just write it in bracket. It's just kind of, what is it? Coefficient of u. Not, it's a scalar. That is multiplied by vector u. Now, if you simplify this, here we have vector v, right? Vector v, they cancel each other. And how about norm of u times norm of u? That's just equal to u dot u, as you know. So here we have u dot v in the numerator. In the denominator, we have u dot u. It's all just a scalar. And outside here, we have vector u. So that is u dot v, u dot v, u dot u times u. That is how we compute the projection of one vector onto another vector. And don't forget that it's also a vector. We are talking about this vector, right? And also some students confuse actually this u, just so they can understand and draw this longer, but it doesn't have to be long. Sometimes we may have this kind of vector. Here we have vector v. How about this one is vector u? Still, when we talk about the projection, we will talk about this vector. That is a projection. Okay. Let's see one example here. Find the projection of v onto u for the given vectors. Let's do only one of them, and the rest you'll practice yourself. Let's do A. So the projection of v onto u. So we need to find the projection of v onto u. That's equal to v dot u over u dot u, right? And times u. Now from here, let's just evaluate here. What is v dot u? And v dot u equals v dot u, negative 1 times 3, it is negative 3, plus 2 times 1, it is 2, plus 3 times 7, that is 21, which is equal to 20. And how about u dot u, right? It is just u dot u, it is 3 squared plus 1 squared plus 7 squared, that's equal to 59. 49 plus 1, it is 50 plus 59. So, and this will be equal to v dot u, it is 20 over u dot u, it is 59, right? And here we have vector u. What is vector u? 3, 1, 7, which is equal to, I can just write here, 60 over 59, or 20 over 59, and here we have 140 over 59. That is the projection of vector v onto vector u. This is how we evaluate this. Okay, gentlemen, that much is enough for this session. So we're finished. Next session we will continue with new one, 1.3. Have some break, okay? After 15 minutes, we will continue. Have a break.